Hello students, my name is Shashank Shekhar. So today we are going to start the chapter that is solution, and today is the first class of that lecture series. So let us start our chapter. So this is the CBSE syllabus that we have. According to the CBSE, we will cover the whole syllabus. So today we'll be mainly seeing the types of solution and the expression of concentration of solution of solids in liquids. So up till this we will cover today. So we will be basically focusing on what type of solution we can have, and then we will see one type of it, that is the solubility of solids and liquids. So let us start the chapter. So if you want, this is the detailed topic of all of those. So first we will see what is a solution and the type of solution, that is homogeneous and heterogeneous solution. Again, we will see the types of solution based on the components that we are having, right? Then in a solid to liquid solution or in any type of solution, we have this something called concentration. So we can represent that concentration in various ways. So first is the mass percentage, then the volume percentage, then parts per million, mole fraction, molarity, molality. So these are very important for your upcoming lectures also, because this will help in most of the chapters, as these terms are important for equilibrium, say equilibrium, or you can say ion equilibrium, or like the thermodynamics. So all these concentration terms are very important, so you should be focusing on this quite well. Moving on to the next topic, that is solubility of solids and liquids. So this is the first type of solution we will see, in which we will dissolve solids and liquids, and then we will see what are the factors that affect this solubility of solid and liquid. Yeah. So let us start our chapter. So first let us understand that what is solution. So what is solution? So if I want to say it broadly, then I will say that, okay, we have two components. First is the solute and second is the solvent. So the solvent is the thing in which we are dissolving the solute, right? Like the example, we can take the example of a sugar solution. So if we are taking water and we are dissolving sugar in it, then the water will be present in excess. In the most cases, water is present in excess. So water will be the solvent and the solute will be the sugar. And the same definition is written here also. So for solute, we can say that a solute is a substance that is dissolved in a solvent. What is this? Dissolved in a solvent to form a solution. While what is solvent? A solvent is a substance that typically in liquid form. So in this chapter or throughout the chapter, we will see that, okay, we are taking most of the solvent in the form of liquid. So this should be kept in mind, and it dissolves the solute in itself. And today together this solution is made up of solute plus solvent. Now one thing comes in your mind, that in some cases we can have more than one solute particles or more than one solute component. Like if you take the example of ORS solution. So in ORS solution we have varied amount of electrolytes, and say sugar, we have glucose also, and some electrolytes which are potassium electrolytes. So some important electrolytes are also present in this say ORS. But so in that case we say that, okay, more than one solute component is present, and it is a multi-component solution. So so this is all about the solute and solvent. So you should keep this in mind, that solute is present in minimum amount, means you can say in a small amount as compared to the solvent which is present in excess. Like the solution we take of sugar solution. So in that case, sugar is present in a small amount compared to this water. So this was all about solution. Now let us see solution on a different basis. So based on the means you can say the concentration in various parts of the solution, or you can say the number of solute particles in various part of the solution, we can divide the solution into two types. The first one is homogeneous and the second one is heterogeneous. So these are the common terms. You must have heard this term earlier also, but I think you should be aware about this thing more clearly, because in this chapter we will see the solution in which all of the solution will be homogeneous solution. and more effectively you can say that binary homogeneous solution. So in this chapter we will be basically dealing with binary homogeneous solution. So what is this homogeneous solution? So first let us talk about this homogeneous and heterogeneous solution. So the first differentiation between these two is that the heterogeneous solution, in heterogeneous solution, all the particles are not evenly distributed in the solvent, or I can say that all the solute particles are not evenly distributed in the solvent, or you can say the solution more appropriately. So consider like we have a solution like ice in soda. So if you put ice in soda water, then the ice will float on the surface of that liquid, but it will not go down on the bottom, or you can say in the middle. So in that case we can say that okay, this ice is not present uniformly throughout the soda water. So that kind of solution will be example of heterogeneous solution. Good enough. Now again we have this soil. In this soil also we can say that okay, soil has various concentration of different minerals and different particles. We cannot just specify them, or we cannot say that okay, this is present 2 molarity or 2 molality. I will talk about this molarity and molality later on. Okay, I'm saying a more simpler word like 2 particles are not present in every soil that we see, that we measure, we can say. So in that case we will say that okay, this is a heterogeneous solution. And if you want a schematic representation of that, so suppose this is our solution. So this thing is representing our solution. Yuck. Okay. And this one is, say this one is the solute particle. So this we are taking a mixture. So we can say that okay, so heterogeneous solution or heterogeneous mixture, it is the same thing. So when we are taking water as the solute and solvent, so basically I mean here that a mixture becomes a solution when we are taking one of the component in excess amount, and that one is termed as a solvent. So mixture is, you can say a solution is a special case of mixture. So I am taking a broader term, mixture here. So suppose we have 2 components. The mixture is made up of 2 components, and here you can see that this is the gray circle. The dark gray circle is representing component number 1, and suppose this light gray circle is representing component number 2. You can see here that the accumulation of component 1 is more here, while the accumulation of component 2 is, this component 2 is more here, and the accumulation of component 1 is less here. So only one particle of component 1 is present here, but here you can see that component 1 is present in excess amount. So you can say that okay, so this region has a different concentration of this component 1, and this region has a different concentration of this component 1. So it is not uniformly distributed. While you can see this one, it's look more like symmetrical, or you can say distributed uniformly throughout the solution. So this, or you can say mixture. So in this case, in this mixture, both component 1 or component 2 are distributed uniformly throughout this mixture. So this is the difference between heterogeneous and homogeneous. Now coming to this chapter, we will take mainly binary solution. So what do you mean by binary solution? Binary solution means we are taking such a solution in which there is one solvent and one solute. That's it. So we will say that we will have one solvent and one solute, and that 2 component will make up this whole solution. So that type of solution will be termed as binary solution. And we are taking not only binary, we are taking a homogeneous binary solution. So homogeneous means the concentration of the solute particle will be uniform throughout the solution. Like we have the example of sugar solution, we have the example of salt solution, or we can have any laboratory solution. So those solutions will have like homogeneous kind of distribution, and they will be binary ones. So we will be dealing with homogeneous binary solution. So this will result in various type of combinations. So if we take 3 states, solid, liquid and gas, and we can combine them in different way. So we can take different combinations like gas, liquid, gas, solid, liquid. So this will total make up 9. How much? 9 type of possible combinations. So it is just a permutation. If you want, you can do it for fun. Okay, so this is the thing. So suppose we have this solute and we have this solvent, right? So we can take different solvents and we can take different solute. So if we dissolve, if we are making a suppose a gaseous type of solution. So one thing I want to make you notice here is that the solvent will always decide the phase of that solution. Why? Because solvent is present in excess amount. So it will be the one which will be deciding that what will be the phase of that solution. So if the solvent is gas, the solution will be in gas phase. If the solvent is in liquid, the solution will be in liquid phase. And if the solvent is in solid, then the solution will be in solid phase. So this should be kept in mind that okay, so whether it does not depend on the solute, what will the phase of the solution, it totally depends upon the solvent, right? So you will remember this thing always. So the solvent will decide the type of or the phase of solution that we are having. So let us start our examples. So if we are dissolving gas into gas, so this gas is the solvent. Suppose we are taking two gases and we are dissolving both of them, and one of the gas is present in excess. So the gas which is present in excess will be the solvent, and the gas which is present in the small amount compared to the solvent gas is solute. Now we can take a mixture of oxygen and nitrogen gas, a very simple and soothing example. So it will be example of gas solution, and one of the gas is taken as solvent. Now next, we can dissolve a liquid in gas. So chloroform, when it is mixed with nitrogen gas, so chloroform is basically CHCl3. So you must have seen in TVs and some dramas that people are using this chloroform to you can say infant people, or you can say subconscious them. So in that case, they use the two phases of this chloroform. One way is that they put in a cloth and they just bring it near to their nose and they get fainted. And the other way is that they can spray some gas or something like that. So in that case, the chloroform is dissolved in nitrogen gas. And so you know that chloroform is liquid at room temperature. So they are dissolving it in gas, that is in the nitrogen gas. And now they are just spraying on the people and they are getting fainted. So this is also an example of liquid dissolved in a gas. So in this case, liquid is dissolved in a gas. Next, we can dissolve solid in gas. So very simple example is camphor in nitrogen gas. So in recent days, people are using this camphor as a room pregnant. So they dissolve this camphor in nitrogen gas and keep it in a bottle and spray it throughout your room so that it can give a nice and pleasant camphor smell. So this is also used in this room pregnancies. So it is an example of solid dissolved in a gas. Next is gas dissolved in a liquid. So the very easy example, this oxygen dissolved in water, and this is a very important phenomena. You know that the whole aquatic system is based on this phenomena. So if this phenomena was not happening naturally, then the whole aquatic system would have been disrupted. So it is this oxygen which helps this aquatic animals to live and to breathe in water. So they breathe this oxygen which is dissolved in water, and at atmospheric pressure there is a certain solution of certain concentration, or you can say certain amount of this oxygen is dissolved in water. So we will talk about this later, that what are the factors that decide the amount of solute that will dissolve in the solvent. Next, the ethanol dissolved in water, which is a liquid solution. So we take a ethanol, we dissolve it in water, and we take it as liquid solution. We can take other examples also. So one of this is milk is dissolved in water. So people all often do this. You can say cow herds, or you do this for their benefit. So they dissolve water in liquids to increase the amount of milk. Okay. And the most common example of a solution which comes to our mind first when we talk of solution is a salt in liquid. So if a person is asked that what is the solution, the first example would hit in mind, it is the sugar solution or the salt solution, which is the example of a solid in a liquid. We can say glucose in water also. Yes, this glucon D and all those energy drinks, those are based on this phenomenon only. We take the powder of a glucon D and dissolve it in water, and we tell that okay, this is a type of hydrating agent. So this is the example of solid dissolved in liquid. Now next we have solid and it dissolves gas in it. So the example is solution of gas in gas, that is hydrogen gas and palladium. So what happens actually? So this palladium surface is a very good adsorbent. So it basically absorbs this hydrogen gas on its surface, and some of this hydrogen gas also, you can say, they also went into or moved to the interstitial side between the palladium atoms, and that will make a mixture of gas dissolved in solid. Next is liquid dissolved in gas, and the most common example is amalgam of mercury and sodium. So this sodium, it is kept sometimes in amalgam of mercury. Sorry. So this sodium, this amalgam of mercury is used in laboratory in some form. So in one of the form is the amalgam of mercury is put on sodium. Next is solid in solid. The example is an alloy. So if we dissolve copper in gold, so copper is dissolved in gold. So it is an example of alloy. So you must have heard this term alloy in your earlier classes also, in 9th and 10th, where you have seen that okay, we have this, say we have the wire of a heater. So that wire should be like this, that it should be a good conductor, plus it should be able to bear a huge amount of heat. So these 2-3 things cannot be found in one metal. So what do they do? Say they take one metal which is having a good conductivity, they take another metal which is having a resistance to this high temperature, and they mix both of them, those in a certain concentration or in a certain amount, that the required properties are gained, and such a thing is called an alloy. And this alloy is a very good example of solid solution, or you can say a solid dissolved in a solid. So we have the example of copper dissolved in gold. So this is also used in making wires of your, so if you are doing, or you can say if you are rich enough to apply this gold as this wire, because it is a very good conductor and provides the minimum resistance. So they, you can say they are very efficient. So this copper dissolved in gold may also be used in this wires. Now next, one more thing I want to say here, that this process of solute dissolving in solvent is called as dissolution. What is it called? It is called as dissolution. So it is a terminology you should remember, that when a solute is dissolved in a solvent, it is called dissolution. Now next, now we will take different terms. Which are used for the concentration medium. So why do we use this mass percentage or this molarity and molality? So in lab we have to perform reactions. Okay, so some of the reactions involve solvent, and we have to dissolve both the reacting particles in that one solvent. So if you want to define something, so if you are dissolving some, if you want to react something, two reactants, so you must have a proper amount of both those, so that they can react and give the required compound or the required material for which you are looking. Now if you do not know what amount of what is present in this solution, what amount of what is present in that solution, then you cannot combine them and get your required solution. So to do that properly, or you can say in a more standard way, that it can be applied throughout the world or in any laboratory that is present in any part of the world or in any university, what do? They take a standard thing that is called solution concentration terms, like mass percentage, like volume percentage, mass by volume percentage, molarity, mole fraction, ppm, and all of those. So each of these have a different type of application in varied amount. So we will see these concentration terms, and these are very important. So they will be used in various chapters also, as I've told earlier. So it has a direct application in various chapters, like our ionic equilibrium, like our thermodynamics, or you can say chemical kinetics. So all of those will have this concentration term, and if you are not concentrated on this, or you are not aware about what is the root meaning of this concentration term, then you will face difficulty. So you should remember this. They are forming the base of all your chemistry that you will be discussing or that you will be studying. So let us start first with the mass percentage. So what is this mass percentage? So if we talk about this mass percentage, so you have heard this term mass percentage very earlier, and you must be very clear about it. So basically what they are doing is here that they're taking something and that calculate, suppose it is having different components, that substance having different component, and you want to quantify each of this component. So what they do, they take the mass of each of those component, divide by the total mass of this component into 100. And you know this thing, you are doing it from the earlier stage also. Total, you got total marks, you divide that total marks, you put that total marks down, and the amount of marks you get out of this total, you put it up, multiplied by 100, you get a percentage. We are doing the same thing here. We are doing nothing more, nothing less, nothing complicated. We are just taking a mass of the component for which we want to determine the percentage, and then we are taking the total mass of the solution and then multiplying it by 100. In this way, what do we get? So if we talk it in a theoretical way, we are getting what is the amount of substance, what is the mass of substance that is present in 100 unit mass of that substance. Simple, clear and crystal and clear. So suppose you have 100 gram of, or you can say 1000 gram of solid, and you have various components in that solid. So that is a solid solution, solid solution. And now you want to say know that what percentage of what solute is present in that. So you take the mass of the solute that is present in that, divide it by total mass and multiply it by 100. So you will get the amount of solute for every 100 gram of that solute. Okay, so I will define it more clearly. So first of all, see this formula. It is simple. If you want to find the mass percentage of a component, you simply take the mass of that component divided by total mass of the solution which contains that mass of that compound, okay, or this component, multiplied by 100. So you will get a mass percentage. So if you want to do understand it by an example, so if a solution described that it contains, means suppose a solution is said that it contains 10% glucose in water by mass. So what does it mean? So it means that 10 gram of glucose is present in every 90 gram of water. 90 gram of water, not solution I am telling you, 90 gram of water. So what will be the total mass? It will be 10 plus 90, 100. So we are saying that 10 gram of glucose is present in 100 gram of solution. And why am I adding this 10 plus 90? You know it. You have studied the first chapter of your class 11, and you are very clear from the that laws of conservation of mass is applied to this simple chemical equations, or you can say processes, and used to describe this processes. So they are called the laws of chemical combination. So I'm using that simple laws of chemical combination, that is the laws of mass action here, and I'm just adding this both to get the total mass. So it should be clear, I think. Now you are saying that you are dissolving 10 gram of glucose in 90 gram of water. So what is the total mass? It is 100 gram. And what is the mass of the glucose? That is 10 gram of glucose. So we are saying that, okay, we are having 10 gram of glucose in every 100 gram of solution. Now this is a varied application. So if you take any industrial product, and in most of those you will find at the back of them that their ingredients, or you can say their components, are described by the mass percentage, that okay, this percentage of this thing is present in this product, or this percentage of this thing is present in this product. So it is used in the industrial chemical applications also for defining the amount of different substances that are present in that product. So for example, if you want to take an example, so bleaching solution, this commercial bleaching solution, so which is used for whitening of clothes, they contains 3.62 mass percentage of sodium hypochlorite. Means in every 100 gram of bleaching solution, we have this 3.62 gram of sodium hypochlorite. That's it. Okay, so you must be clear about that. So this is called as the mass percentage, and this is the theoretical meaning of this. If you want to take it in the way of a unitary method, you can also do so. So let me define it with the help of unitary method. So suppose we say, let us take an example that okay, we have a gram of solute. I am taking kg for avoiding confusion. I'm taking an x, right? Now x kilograms of solute is dissolved in how much gram of solvent? Y gram of solvent, right? And you have to find that what amount is present in 100 gram, right? Sorry, let me take a solvent here. X kg of solvent contains 4 gram of solute. Now you have to find it for 100. So first we will find it for 1. So 1 kg of solvent will contain y by x gram of solute. It should be clear. So how much will 100 kg will contain? 100 kg will contain. So this, both of these units should be same. Yeah. So 100 kg of solvent contain y by x into 100 kg of solute. So you can define it using the unitary method also. You do not need to remember it. I'm just telling it for information that it is not an new, or you can say a complicated thing. It is simple application of this percentage, or you can say this unitary method. So do not get confused with it, right? Now in the same way we can have this volume solution. There is nothing more added to this new thing. So we have this volume percentage. So if you want to define it, it is defined in the same way as the mass, only we are replacing this mass with volume, right? So what is the volume percentage of a component? It is the volume of the component divided by total volume of the solution multiplied by 100. So it will be termed as volume percentage of a component. Now it is represented as V by V, right? So if you want to take an example, so we can take this, that okay, we are taking 10% ethanol solution in water. So what do we mean by this? We mean that okay, we are having 10 ml of ethanol dissolved in water such that the total volume is 100 ml. So what we are doing, we are taking a solution that is 10% ethanol solution. So it means that in every 100 ml of solution there is 10 ml of ethanol, or we can say that 10 ml of ethanol we are taking, and I'm taking an ideal case here that okay, the overall volume of the solution will remain same. It does not happen so, because ideal solution is just hypothetical solution. So I'm taking an ideal case that okay, we are taking 10 ml ethanol and we are dissolving in 90 ml of water, then it will result in 100 ml of solution for the ideal case. So it will be termed as 10% ethanol. Now solution containing liquids are commonly expressed in this unit. So that mass thing I was talking about was usually used for this multi-component or multi-phase type of solution. Yeah. So more specifically I can say that it is used for multi-phase solution if we are having a solution such that It is having solid also in it. It is always having gas also in it. It is having liquid also. So for that we use this mass percentage. But for the liquid solution, this volume percentage is more appropriate. So example, if we have a 35% weight by volume solution of ethylene glycol, and antifreeze is used in car for cooling the engine. At this concentration, the antifreeze lowers the freezing point of water to 255.4 Kelvin. So here is a very good example of how this concentration term is used to make our life easier. So what does this mean? So it is saying that we take a 35% solution of ethylene glycol. And what does this solution contain? This contain ethylene glycol plus water. And what is the concentration of volume by volume percentage of this ethylene glycol? That is 35%. Means in every 100% of this solution containing ethylene glycol and water, we have 35% of, or you can say 35 ml of ethylene glycol. That's it. And what it is used in antifreeze. So it lowers the freezing point of water to 255.4 Kelvin. So you know it very well that, so if you convert it in this Celsius, you will get this amount, which is minus 17.6 degrees Celsius. So you know very well that 0 degree Celsius is the freezing point of water. But when this say ethylene glycol is added in water, it lowers its freezing point to minus 17.6 degrees Celsius. And what is the concentration that we are taking? We are taking 35%. Means every 100 ml of this solution will contain 35 ml of ethylene glycol. Now how does this reduces this freezing point? We will see later on. So we will have the discussion of this colligative property later on, and you will see it very clearly that why it is happening such. So this is the volume percentage. Next we have this parts per million. Now this parts per million is also an application. So each of this will have application, and we'll see it one by one. So what is this parts per million? So this parts per million is used in that case in which the solute is present in a negligible amount, in a very small amount. Like if you want that, okay, we have to decide what is the amount of toxicity or intoxicant that is present in water, or you can say in air. So they are present in very small amount. I am not saying that it is small amount means not harmful. That small amount is sufficient enough to destroy your healthy life. So I am basically, what I am saying is that their amount is present in trace. So very little amount of those are present in that whole bunch of that gas. But you must have the knowledge of it, because that small change in that percentage also, or in amount also, can have a hazardous effect on your health. So to study that, we have introduced a small type of unit or concentration, that is parts per million. So what does it say? It says that what is the number of component that is present in total number of all component in 10 to the power 6 parts. So I will define it more clearly. So let us understand it by an example. So let the total number of all components of the solution, as in this case of percentage, is parts per million, can also be expressed as mass to mass. So earlier we are saying that, okay, we were taking in 100 what amount is present. So suppose something is present in very small amount. So if you are taking 100 ml of that, or 100 gram of that, then the amount of solute that is present in that 100 is very small, and it is not appearing in your calculation. So we cannot, it is not will be a easy way to define the concentration. So what we do, instead of taking 100 gram of 100 ml, we take a million gram or a million ml. So suppose 100 is containing, I am saying that suppose 100 gram is containing 0.001 gram of this solute. Now if I want to find it for billion, will contain 10 to the power 6. So I'm writing just 10 to the power 6 here. So if you want to calculate for 10 to the power 6, then it will be 0.0001 divided by 10 to the power 2 multiplied by 10 to the power 6. Okay, right? So it will more appropriately, or you can say you can get a significant number or a large number that will be easier to handle. So what the number you will get, it will 10 to the power 4, will get 1 gram of solute. So you can see here that now, okay, we do not have to deal with this small number, and rather than this we can use our 1 gram that is dissolved in 10 to the power 6 gram. So this is the main purpose of this parts per million. So if you are having something in a trace amount, you will simply take parts per million. We have also one more term which is closer to this. It is called ppb, that is parts per billion. It is greater than this million, so you do not have to worry about this. I'm just telling it for your information. So it will be 10 to the power 8 or something, and this pp parts per million is denoted by ppm. Now let us take an example to understand it. So this parts per million can be for anything. So if you can take it for volume, you can take it for mass, that what percent mass of is present in 10 to the power 6, mass what volume is present in 10 to the power 6. So example, so a liter of seawater means 1 liter of seawater contain 1030 gram, which weighs 1030 gram, contains 6 into 10 to the power minus 3 gram of dissolved oxygen. So what we are saying is that a liter of water which has a mass of 1030 gram means 1030 gram contains 6 into 10 to the power minus 3 gram of oxygen. So such a small concentration is expressed in ppm. So instead of saying that okay 6 into 10 to the power minus 3, we take it as this small concentration as this 5.8. So it is 5.8 is gram is present in every 10 to the power 6 gram of this water. So this is the mass of water, and this is the mass of solute, right? So this is obtaining from the unitary method. So if you want to take it out, if it is very easier, so what we are doing is that here it is said that okay 1000, or it is written that this amount of water contain 6 into 10 to the power minus 3 gram of oxygen. Now 1 gram of water will contain 6 into 10 to the power minus 3 by 1, right? Now we have to take it for 10 to the power 6. So it will be 6 into 10 to the power, so it is 1030 minus 3 by 1030 multiplied by 10 to the power 6. So if you just calculate it, so it will be subtracted. It will be 10 to the power 2, right? So it will be 6 by 103 into 10 to the power 2. If you calculate it, you will get 5.8 ppm. So it is mainly used in that cases in which we have a small amount of solute dissolved in a large amount of solvent. Now one more thing here, we can also tell it as mu gram per ml, right? We can also tell as mu gram per ml. So mu means 10 to the power 6 minus 6, right? Okay, so this was the thing about parts per million. Now comes a more important thing. So this is mole fraction. Mole fraction. First thing, important thing about mole fraction, commonly used for gases. So it is commonly used for gases, right? Now what is this mole fraction? So for mole fraction, you should be clear about how to find the number of moles. That is, for those who don't know, it is given mass by molar mass. As simple as that. So if you have a given mass, you divided by the molar mass, you get a number of moles. Now if you want to find the mole fraction of a component, then you have to take the number of moles of that component that is present in that solution divided by total number of moles of the component, right? So this will give you the mole fraction. Now let us take the example of a binary mixture. So I have told you earlier also, we will take mostly the binary mixture, and suppose it contain a number of moles Na. So A is having Na number of moles and B is having Nb number of moles. So what will be the mole fraction of A? So it will be chi A is equals to, so it is chi A. So do not get confused. It is like this, chi A. I have written it here also. It is represented by chi, and in subscript we have this A, for whose we have to find the mole fraction. It will be chi A is equals to number of moles of A by total number of moles, that is Na plus Nb. Now if we talk about not binary mixture, a multi-component mixture, so how we'll define it? So if you want to take a mole fraction of any of the ith component, so it will be chi I is equals to Ni by N1, N2, N3 up till Ni, right? It will be Ni by chi Ni. Now one more thing, like if we add all the fraction, it will be 1. You know this. Yeah, it is very clear from your primary school knowledge also. So if we have a cake, we take 1 by 4 part of it. So we divide it in 1 by 4, 1 by 4. And if we add all those cuts, or you can say pieces, you will get your whole cake back, one cake back. So this is a primary example. You can relate directly to the mole fractions. So you're taking the fraction of one of the component. So if you add all those components fraction, you will get one, absolutely one, right? So it should be clear that the addition of all the mole fraction will be equals to the unity. Now it is very useful. This property is very useful for binary solution. How? So let me show you how. So if you have Na and Nb, two particles of A and B, right? Then what will be the mole fraction of A? It will be Na divided by Na plus Nb. Now you know very well from the property I have told you just now that mole fraction of both this component will be equal to 1. So if you want to find the chi of B, that is mole fraction of B, so what will be it? It will be 1 minus chi A. We will take this here, or we can say that 1 minus Na plus Nb. So if you do this, you will get your answer. If you want to prove, you can prove it also. So it will be Na multiplied by Na plus Nb, sorry, 1 multiplied by Na plus Nb minus Na plus Nb. So this Na minus and Na plus will get cancelled, and you will get your Nb. So if you have mole fraction of A, you can just subtract 1 from it. Or sorry, if you have a mole fraction of B, you will subtract this term from 1 and you will get your chi 1, but chi A. But the thing that should be kept in mind is that it should be a binary solution. Only 2 of the components should be present. Then one of those can be found out by subtracting 1. Clear? Right. Next terminology, molarity. So what is this molarity? So if you want to define molarity, it is simply, so this is the most important term. Be clear about it. You should be very clear about it. Okay, so this will be used multiple times in your every calculation, every chemical equations and all, and every reactions. So including all those, it is very important. You should be quite clear about it. So what is this molarity? It is the number of moles of solute that is dissolved in 1 volume liter of that solution, or you can say 1 liter of that solution. So how do we find it? So suppose 30 liters are containing 20 moles of that solution. So 1 liter will contain 20 by 30, simple as that. So we are doing the same thing here. We are dividing the moles of solute divided by the volume that is containing that moles of solute. And the important thing to notice here is that the volume of solution should be in liter. So it is important that the volume of solution should be in liter. Now this is the formula. The application will be cleared through this questions. So we will discuss these questions later on. But for the time being, let us take a simple example. So if we are taking a solution that is having 0.25 of mole dissolved in 1 liter of solution, or we can designate it like this also. So it is also a proper terminology, and it will be used only. It will be only used throughout the chapters and all. So it is represented at 0.25 m, and that is also capital M. So it is saying that it is present in molarity terms, or the concentration is termed as molarity. So if we say this, so we are saying directly or theoretically that we are dissolving 0.25 mole of NaOH in 1 liter of solution, or in 1 cubic decimeter. So why I'm saying this decimeter? So you should be knowing that 1 liter is equals to 1 decimeter cube. What is this 1 decimeter cube? It is the volume that will be occupied by a cube that is having 1 decimeter length, 1 decimeter height, and 1 decimeter width. So that we are taking the volume like this. So 1 into 1 into 1, and decimeter will be 3 times, so it will be decimeter cube. And 1 liter is equals to 1 decimeter cube. So this conversion is also very important. It will be a helping hand for oral calculations. Now one more thing here. Sometimes this liter here is taken as milliliter. So in that case, this M becomes millimole. So you will see this term often. So do not get confused. Okay, right? So children say that what is this millimoles, and what about this millimole? So it is nothing but the solution in that case is taken in not in liters but in milliliters. So we said it that this millimole or this millimolarity. Next, we have this molality. So only the difference you can say is L. You have replaced this R by L, but it is very different in terms of technicalities. So if you want to define molality, first of all, this is represented by small m. So if you want to say something is present in molality, suppose we have 2 molarity, we will say that 2 small m. And while in molarity we have 2 capital M. So it is the difference. So you should be keeping this in mind always, that okay, when we are saying that molarity, we will take it as capital M, and when we are saying that molality, we will say it as small m. So how it is defined? It is the number of moles dissolved per kg of the solution. Note, the thing to note is per kg of the solvent. Yeah, 2 things to notice here is that first, the unit of this mass should be in kg, that is present in the lower fraction, and we are taking the mass of solvent and not the solution. So it is the number of moles of solute dissolved in 1 mass, or you can say 1 kg of this solvent. So in the lower fraction we have this solvent mass, and that is also in kg. For example, we say that okay, we have 1 mole per kg of a solution, or 1 small m of the solution of KCl, which means that every 1 kg of water will contain 1 mole of sodium chloride, or 1 mole of sodium chloride, its molar mass is 74.5, so it will be 74.5 gram of KCl in 1 kg of water. Now the thing to here is notice that each method of expressing concentration has its own merits and demerits. Yes, so this molarity is used in different places and different cases. So all these fractions are made. Now one more thing, the most important thing, molarity is used always. You have seen it earlier also. Why molarity is used? Because it is temperature dependent, and we know that reaction is affected by temperature. So if something is not changing with the temperature, it will be not appropriate to use it for the reaction. So we use this molarity which changes with temperature. So we always use this molarity. So why do we use this molarity, and why molarity is not change? Why do molarity changes with temperature and molarity does not? Because the reason is very simple. Molarity, we are taking the volume. Molality, we are taking mass. And mass doesn't get much more affected by temperature, but volume does, because we know the ideal gas law and all those laws, that okay, when volume is increase, decrease, it as temperature is increase or decrease. So if you change the temperature, you will change the volume, of course, in every way. So molarity is more preferred. Now we'll take the solubility of solid in gas. So what we are doing is we are dissolving, first case, we are taking the first case, we are dissolving a solid in liquid. So one thing to keep in mind is that we are should be aware of this also always, that in most of the solution, one rule is applied and it will be applied always, that a solution is made only and only if we are dissolving like in like or unlike in like, unlike in unlike, like this. If you are taking sodium chloride, which is a polar, we will dissolve in water. We will not dissolve in benzene, which is a non-polar one. Similarly, if we are taking water, we cannot dissolve chloroform in it because chloroform is not that much polar. So it should be kept in mind. Next, the terminology is related to the solvent solubility of solid in liquid. The first is saturated solution. So what is a saturated solution? A saturated solution in which no more solute can be added at that given temperature and pressure. These two things should be same. So you will not say that okay, we are varying the temperature and then we are introducing more solute, so it is not a saturated solution. So it is a saturated solution at that given temperature and that given pressure. And the reverse of that, unsaturated solution, means more of the solute can be added in that solution. Now I will tell you one more thing now, right now, and it will be used in your equilibrium part also. So this thing is called solubility. So if in a saturated, sorry for the mistake. Sorry for the mistake. So if you are taking a saturated solution, then you will say simply that the concentration of solute is the solubility. It is represented by S. So what is the definition of solubility? So solubility is the concentration of a solute in a solvent when the solution is made saturated. One more time. So what is solubility? The solubility is that concentration of solute which is dissolved in solvent when the solution is made saturated, and saturated means no more solute can be added in the solvent at that given temperature and pressure, right? So this is all about the solubility of solid and liquid. Now one more thing here, factors affecting. So first is the effect of temperature, and this effect of temperature is a direct consequence of Le Chatelier principle, which says that okay, so if we do a change in an equilibrium, so that reaction or that process will move in that way such that the effect of the change can be minimized or it can be tend to the negligible amount. So how do we use it to define the effect of temperature? So very simple. So if we are taking a saturated solution, nearly saturated solution, and the dissolution process, I have told you what is dissolution means, dissolving that solid into solvent, is endothermic, means the energy is taken in. So if we increase the temperature, the solubility should increase. Simple. So if we increase the temperature, so what will happen? The solubility will increase and the solute will be dissolved in solvent, and we know that since the process is endothermic, it will take that extra temperature rise heat and bring the temperature back to the initial temperature. So it is only the Le Chatelier principle because it is minimizing the change. Similarly, the reverse of it is also true. So if you are taking an exothermic solution, so the solubility will of course decrease because now the temperature has been risen. So if you want to lower the temperature, so what will do? It will sorry. So if we have the exothermic reaction, so the solubility will decrease if we rise the temperature because it is giving you heat, and in the reverse process it will take the heat. So what will happen? So if we increase the temperature, so it will move in reverse way so that the extra heat will be taken. And what is the reverse way of dissolution? The dissolution reverse process will give us solvent and solute back. So that is the thing here. So you can apply directly to this, say, solid in liquid form. So you must have seen that if we freeze the sugar solution, you will be able to see the solute or the sugar particles uh, precipitating or coming out of the solution. So it is a direct effect of this effect of temperature. So if you have not done this, you can do this in your home also. Take a solution of sugar, dissolve sugar in it, excess amount. You can take a saturated solution or nearly saturated solution. Now keep it in fridge. So after some time you will see that the temperature is reduced, and since it is an exothermic process, for knowledge I would want to say that it is a exothermic process. So as the temperature will fall down, the solubility will decrease and the sugar particles will come out of the solution and the solubility will decrease. So this is clear. Yeah, right. Now if you move to the effect of pressure, so pressure has negligible effect on the solubility of solid in gas. Why? Because we know that applying pressure to a solid is like doing nothing to it. So more literal way we can say that we are doing nothing to that solid if we are applying pressure on a solid. So if we are dissolving solid in a gas and you are applying pressure, so it will have a negligible effect. So this solubility has of solid in gas have no effect of pressure. So that was all for today's class. So thank you for your time. So we will continue this chapter later on. So in the next slide and then in the next lecture, where we will see the solubility of different solute in solvent. The first we have completed the solid in gas. We will take different laws are also being formed for this solubility cases. So we will see those in the later lectures. Thank you.